Everyone, today we are going to solve some important numerical problems from the chapter electric potential. So let us now start with question number 1. Two thin wire rings, each having a radius r, are placed at distance d apart with their axes coinciding. The charges on two rings are plus q and minus q. Find the potential difference between the centers of the two rings. So here we have centers of the two rings, center A and center B. Okay, we have to find the potential difference VA minus VB. So first of all, we will find the potential at A. Potential at A can be calculated by taking the algebraic sum of potentials due to plus Q charge and minus Q charge, which is given by VA equal to K into Q by R plus minus Q by root under R square plus D square, and the same concept will be utilized to find the potential at B. So potential at B, that is VB equal to K into minus Q by R plus Q by root under R square plus D square. Now to find the potential difference between the centers A and B, we will have to calculate VA minus VB. Okay, we will have to calculate VA minus VB, which is given by K into 2Q by R minus 2Q by root under R square plus D square, which is Q by 2 pi epsilon naught 1 by R minus 1 by root under R square plus D square. So this is the answer. Now in question number 2, three charges capital Q plus Q and plus Q are placed at the vertices of a right angled isosceles triangle as shown in the figure. The net electrostatic energy of the configuration is 0 if Q, that is capital Q, is equal to. Now 4 options are given to you. You have to select the correct option. So let us try to find the electrostatic energy of the configuration. So here the electrostatic energy of the configuration can be written as U equal to K Q by A. Here you can see Q and Q divided by A plus Q by root 2A plus capital Q small q by A equal to 0 according to the given condition of the question. Now we solve it and find the value of capital Q as minus 2Q by 2 plus root 2. Now in third question, in the electric field of a point charge Q, here the charge Q is placed. A certain charge is carried from point A to B, C, D and E as shown in the figure. The work done is. Now you have to select the correct option. What about the work done? Okay, so here we see that all the points A, B, C, D and E are on the equipotential surface. This is the equipotential surface, and all the points lie on the equipotential surface. That is why potential at A equals the potential at B, potential at C, potential at D and potential at E. So work done dW equal to Q dV equal to 0 because potential at all the points is same. In question number 4, in an electric field of a point charge Q shown in the figure, a charge capital Q is carried from A to B and from A to C. Okay, from A to C, from A to B. Now what will be the work done? 4 options are given to you. You have to select the correct option. So here we find that WAB, that is work done in carrying a charge capital Q from A to B, and WAB is given by Q into VB minus VA. Then we find the work done in carrying the charge Q from A to C, which is given by WAC equal to Q into VC minus VA. Since VB equal to VC, that is why WAB equal to WAC. This is the correct answer. In question number 5, two charges Q1 and Q2 are placed 30 centimeter apart as shown in the figure. A third charge Q3 is moved along the arc of a circle of radius 40 centimeter from C to D. The change in potential energy of the system is Q3 K by 4 pi epsilon naught, where K is. Now you have to find the value of K. So the given condition is that the change in potential energy of the system is given to us. So we can write the change in potential energy as delta U equal to UF minus UI. Here UF is the final potential energy of the system and UI is the initial potential energy of the system. So we find that the value of final potential energy is 1 by 4 pi epsilon naught Q1 Q2 by 0.3 plus Q2 Q3 by 0.1 plus Q3 Q1 by 0.4, and the initial potential energy is given by 1 by 4 pi epsilon naught Q1 Q2 by 0.3 plus Q2 Q3 by 0.5 plus Q3 Q1 by 0.4. Now according to the given condition we put the value of change in potential energy of the system equal to UF minus UI. Thereafter we calculate and find the value of K as 8Q2. In question number 6, charges plus Q and minus Q are placed at points A and B respectively, which are at distance 2L apart. C is the midpoint between A and B. The work done in moving a charge plus Q along the semicircle CRD. So in this way we have to move the charge and we have to find the work done in moving that charge. So work done in moving the charge capital Q along the semicircle CRD is given by W equal to Q into Vd minus Vc. So let us try to find the potential at point D. Potential at point D is given by K into Q by AD plus minus Q by BD. Here we have minus Q by BD and Q by AD. So potential at point D has been calculated and its value is minus Q by 6 pi epsilon naught L. The value of K is 1 by 4 pi epsilon naught. Now potential at point C. So we see that point C is the midpoint of AB, that is why AC equal to CB. Now we find the potential at point C due to charge Q and minus Q, which is given by K into Q by AC plus minus Q by BC. Since AC equal to BC equal to L, so potential at point C is 0. Now W equal to Q into Vd minus Vc, putting the value of Vd and Vc, we find that work done is minus Q by 6 pi epsilon naught L. In question number 7, n small metal drops of same size are charged to V volt each. If they coalesce to form a single large drop, then its potential will be. Now you have to select the correct option. So when all the small drops combine together to form a bigger drop, then volume remains the same. So let us suppose that radius of bigger drop be capital R and radius of a small drop be small r. So equalizing the volume for the bigger drop and smaller drop, we find that 4 by 3 pi r q equal to n into 4 by 3 pi small r q. This gives a relationship between capital R and small r. So capital R equal to n to the power 1 by 3 into r. Now since each metal drop is charged to V volt each, so potential of small drop V equal to K into Q by R. And let us suppose that V dash be the potential of bigger drop, which can be written as V dash equal to K N Q by R equal to K N Q by n to the power 1 by 3 into R. Here we have replaced the value of capital R in terms of small r and we find the value of potential of bigger drop, that is n to the power 2 by 3 into V. So this is the way to solve the numerical problems. I hope you might have understood all the concepts. Now you try some more problems on your own. Okay, thank you.